Greetings everybody and welcome back to another exam video. Today we're taking a look at the multiple choice section of the 2018 Methods Exam 2. So let's jump straight into it. First of all, we got a nice and simple question. We have a CAS graph over here and we're just asked to find the period of this guy. How to do that? You just take 2 pi and divide by the coefficient in front of the x there. In this case, you do have to be a little bit careful because it's 2 pi divided by 3. The 2 pi's are going to cancel and we're left with a 3 on the denominator of the denominator, but that just flips up to the numerator to give you a 3. So the answer is C. Question 2. We want a maximum domain of a function to be all the real numbers except for 1. First of all, we have option A here. That's probably the correct one because we have an x minus 1. That means an asymptote that x equals 1. B wouldn't be an option because the asymptote would be at x equals 5. C could be an option because if you... actually, C is not an option. What am I talking about? Because you can't get a 0 on the denominator there at all. D wouldn't be an option either because the asymptote is x minus 1. And E wouldn't be an option because square roots have no asymptotes. Actually... the square root over here, the maximum domain is from 1 to infinity, not all real numbers excluding 1. Alright, question 3. We have a hyperbola, so let's draw this. The hyperbola looks something like this, and on the other side as well. And A and B are positive real numbers. So we have A, let's say, and B. And we want to find the range of this guy on the interval A to B. So we include A, but we exclude B, like so. So what's the range going to be? Well, we have 1 over A, which is going to be the upper bound, and then 1 over B, which is going to be the lower bound over here. So it's 1 over A, 1 over B. We want 1 over B before 1 over A, so it's looking like option C or D here. And we want exclusive on 1 over B, so it has to be D. Alright, question 4. The point A, which is 3, 2, lies on the graph of the function f. Now the function f is transformed to the graph of g via this transformation, and we want to find the image of this point. What's the corresponding, image point of 3, 2? So how do you do that? Well, let's first understand the transformations of this graph g. So what are we doing here? We first apply the dilation by a factor of a half from the y-axis. So 3, 2 gets turned into 3, 1. So all y values get switched down by a factor of half. Okay, and then we have an x minus 1 in here that just tells us that we're translating to the right by 1 unit. So this 3, 1 turns into a 4, 1. So it's going to be option C. Alright, question 5. Consider a function f, which is x squared plus p over x, where x is not equal to 0. We know there's a stationary point on f when x equals 2, and we want to find the value of p. Okay, there's a nice and simple way to do this on the CAS. What I'll do first of all is, we could define the function. Let's do that. So let's define f of x equals, it was x squared and then plus p over x. Okay, and what do we want? We want a stationary point of f when x equals -2. So what we want to do is we want to solve the derivative with respect to x of the function f of x, and we want this derivative to be equal to 0 when x equals -2 because there's a stationary point there. So we're going to set this equal to we're going to set this equal to 0, but we want x to be equal to -2. Okay, and what are we solving for in particular? Well, we know what x is equal to, so we're not solving for x, we're actually solving for p. We're trying to find the value of p such that this derivative is equal to 0 when x equals -2. So p equals -16. So it's going to be option A. Question 6. Let f and g be two functions such that f is 2x and g is, well actually g of x plus 2 is 3x plus 1. Okay, so we like to understand, well, g of x. What exactly is g of x? Well, we have the x plus 2 there, which I don't like. So what I'm going to do basically is replace all instances of x with x minus 2. And the reason why I replace x with x minus 2 is, well, because I want to get rid of this extra plus 2 here. So if I replace this x in here with an x minus 2, that's just going to give me an x inside of the g. And I need to do the same thing on the right hand side. So we have x replaced with x minus 2. So we have this guy here. So that means we have 3x minus 6, and then plus 1, so 3x minus 5. Okay, and we're just asked to find f of g. F of g, well, f is just taking 2 times the input. If you do f of g of x, then you're just taking 2 times g, so 3x minus 5. That's exactly 6x minus 10, so it's option D. Moving on, question 7, we have a log graph, or a log function. It's log base 2, and what do we know about this guy? We know the inverse of the number 1 is equal to 8. Alright, there's a few ways you can do this. It's probably, you could find the inverse of this guy and work using the inverse function, but it's probably better just to invert this equation over here and to realize, first of all, log is invertible. It has an inverse, so you can rewrite this as f of 8 equals 1. So essentially what you're trying to do here is you're trying to find the value of k so that f of 8 equals 1, which isn't too tricky to do. We can do this on the CAS. We can define f of x to be equal to k times, and we're going to take the log base 2. So where's log base 2? It's over here. Log base 2 of x. I believe that should be it. Yep. And then what we're going to do is we're going to solve f of, now what do we want to solve for first of all? We want to solve for k. And we're trying to find the value of k where f of 8 equals 1. So I'm going to type in f of 8 equals 1 here, and we're going to find the value of k which does this. K equals 1/3. Question 8, we have some integral equations over here. Okay, so the integral from 1 to 12 is 5. The integral from 12 to 5 is -6. Whenever I see reversed bounds over here, I like to reorient that. In particular, we can just multiply everything by negative, and that reorients the bounds into the correct direction. So it's 5 to 12 now of g of x and dx, and this is going to give us 6. We want to find the integral from 1 to 5. How do we get that? Well, the integral from 1 to 5 of g of x dx is equal to, you can just take the difference of these two guys over here. In particular, it's the integral from 1 to 12 of g of x dx. That gives you the area from 1 to 12, but you don't want the area from 1 to 12, you only want the area from 1 to 5. So you cut off the excess there, which is the integral from 5 to 12 of g of x dx. And what is that? Well, 1 to 12 is 5, minus 5 to 12, we just found is 6, so it's -1. Question 9. A tangent to the graph of y equals log e2x has a gradient of 2. The tangent will cross the y-axis at. Okay, so we're trying to find the gradients, we're trying to find the points on this graph over here, which has a gradient of 2, and we want to find the tangent line at that point. And there's a nice program that does this. I just realized we haven't even used programs yet, and it's already question 9. So I'll use my CAS programs for that. If you're interested, link in the description. But we'll go to methods, differential calculus. I'll go to solve tangents, and I'll type in, what is it? Log base e of 2. So ln 2x, comma x, and I'm interested in a gradient of 2. And I should really modify this program so you don't need to put in infinity, negative infinity and infinity. Maybe they'll come up in a new update or something. And we found a point with a gradient of 2. Here it is. There's the equation of the tangent line, and there's the y-intercept. It's -1. If you don't have the programs and you still want to know how to do this question, well, here's how you do it. What you do first of all, let's define the function. So I'll define f of x equals ln 2x. Okay, and what I'm going to do now is I'm going to try to find the point where this function has a gradient of 2. And you do that by doing solve the derivative of f of x equals 2 with respect to x. We get x equals to 1/2. And then you'll just use the tangent line command on the CAS. So we'll go to calculus, then tangent line. And we want to find the tangent line of f of x with respect to x at this point here. That did not work. There we go. Could you do x comma x? That doesn't work. So you could put it in that way, or it has to be like this. So the y-intercept is -1, which is what we're after. Okay, question 10. The function f has the following property, so it's a functional equation. Which one of the following is a possible rule for the function? So right away, what I'm thinking is, let's rearrange this guy over here, so we just get all the functions on one side, so it's f of x plus f of x. This question is outside of the study design now, actually, so I guess you don't have to worry about this one too much, but yeah, it's still good to know how to solve these sorts of questions. So this is equal to 0. Basically, what I'm going to do is I'm going to define my functions, and for each of these functions I run through, I'm just going to evaluate this expression, and if it gives me 0, then I know I got the right function. That's why I put everything onto the left-hand side, so that I just need to evaluate one expression, and just see if it gives me 0 or not. I don't have to evaluate both sides of this equation. So let's define f of x to be equal to 1 minus x, and I'm going to take a look at f of x plus f of x, and then minus f of 2x. Okay, that's the expression. Let's click enter. That doesn't give me 0, so option A is wrong. I'm going to go to x minus 1 now. Evaluate the expression again. It's not 0. Redefine. It's just x. Reevaluate the expression. Oh, it's 0. So it could be option C. Let's just make sure it's not any of the others. So next up we've got x over 2. And I'm going to reevaluate that expression. It's x equals, it's not 0. And finally, 1 minus x over 2. So do 1 minus x over 2, reevaluate, it's not 0, so it has to be option C. That was the only one that gave me 0. Alright, question, what are we up to? Question 11. The graph of y equals tan ax, where a is a positive number, has a vertical asymptote at x equals 3 pi, and has exactly one x-intercept in the region 0 to 3 pi. So let's draw out a little graph of what's happening here. So here's my x-axis, and what do I know about this? I know that I have a vertical asymptote at 3 pi. Why is the zoom not working on this? So here's my x-axis. Something's going on with this. Oh dear. So here's my x-axis, and then I know I have a vertical asymptote at 3 pi. So here's my 3 pi asymptote, and let's say this is 0 somewhere over here. That's 0. Okay. Because this is tan of ax, we don't have any horizontal translations, so we can assume that there's also another asymptote here. That's x equals negative 3 pi, just because of symmetry. And well, what could our graph look like, first of all? It could look like this over here. But this wouldn't be an option because, as you can see, there's no x-intercept on the interval 0 to 3 pi. There's an x-intercept at 0, but that's not on this interval we're interested in. So that means, well, first of all, we can't really dial out our graph out even further. Well, first of all, it's going to cross these asymptotes anyways, which we don't want. So another possibility is that we have an extra pair of asymptotes in here at x equals pi and x equals negative pi. So right in there. So in this case, if we draw our tan graph now, it's going to look something like this. And in this case, it does make sense because now we still have an asymptote at x equals 3 pi, and we get an extra intercept in there as well. We just got to figure out, well, what's the a value for this type of graph here. And just looking at this, you can tell that the period is exactly 2 pi. How to calculate the period for a tan graph? It's exactly pi divided by the coefficient in front of x, which is a, and we want the period to be 2 pi, so this means a must be equal to 1/2. So it's option C. Question 12, the discrete range variable has the following probability distribution. Let mu be the mean of x, and we want to find the probability that x is less than mu. Alright, so let's find mu first of all. We can use discrete info for this. Hopefully you guys already know how to do it manually, but if you have the programs, you can go to discrete info, which is over here, and we'll type in the list of x values, so 0, 1, 2, and 3, and 6. Okay, and then we'll type in the list of probabilities as well, which is a quarter. We have 9 on 20, we have 1 on 10, and we also have, I'll put an extra comma there, we also have 1 on 20, and we also have 3 on 20. And that gives us a mean of 17 on 10. Let's approximate that by pressing Ctrl Enter. The mean is 1.7. So we want to find the probability x is less than mu, which means x is less than 1.7, but that just means it's either 0 or 1. So we want to do 1/4 plus 9/20. 1/4 plus 9/20 is precisely 7/10. Alright, so it's option E. Question 13 now. In a particular scoring game, there are 2 boxes of marbles, and a player must randomly select 1 marble from each box. So I imagine 2 boxes now. Here are my 2 boxes. Okay, so we're going to select 1 marble from each box. The first box contains 4 white marbles and 2 red marbles. Okay. Maybe I should actually do that in red, just so we can see it's better. So 2 white, 2 red, even though that's not white, but I don't want to use white on white backgrounds. The second box, so box 2 over here, what does that have? Contains 2 white marbles. So we have 2 whites and 3 red marbles. 3 red. Each white marble, white, scores -2 points, and each red marble scores us 3 points. The points obtained from 2 marbles selected randomly by a player is added together to obtain a final score. And we want to find the probability that the final score is equal to +1. So, if we're only selecting 1 marble from each box, so that's 2 marbles in total, the only way for us to get a score of +1 is if we get 1 red marble. So what do we want over here? We want 1 red marble, and we want 1 white marble, because 3 plus -2, that's going to be 1. Okay, so we're just going to find the probability of picking 1 red marble and 1 white marble in any order. It doesn't really matter. So how do you do that? Well, first of all, you could have a white marble and then a red marble in the second box. So what's the probability of that happening? It's going to be something like, well, the probability of white marble in the first box is exactly 4 and 6, or 2/3. And then you multiply that with the probability of selecting a red in the second box. That's going to be 3 out of 5, I believe. So 3 on 5. And then we want to add this with, so that we did white and red, now we want to do red then white. So the probability of picking red in the first box is 1/3, and then white in the second box, that's going to be 2/5. And if we evaluate everything, that's a 6 plus 2 over 15, that's going to be 8 on 15. So the answer is C. Sorry, E. Okay, question 14. We have A and B are independent events, so right away when I say independent events, my mind jumps to probability of A intersect B equals probability of A, probability of B, where probability of B is twice the probability of A. Okay, so we can make a substitution here maybe. So PRA, well, this is PRA squared, and then we have 2 of them. So we just substitute that equation in, and we also know the probability of A union B is equal to 0.52. Okay, but now we can use the addition rule. Whenever you have intersections and unions involved, it's probably addition rule. So addition rule goes like PRA plus PRB, and then minus PR of A intersect B. Now we want to find the probability of A here. So we know what the left-hand side is, it's 0.52. So let's rewrite this. So this is PRA plus PRB. We know PRB is twice PRA. And minus the probability of the intersection, which is 2PRA, but squared. Okay, but this gives us the equation. 0 equals 3PRA minus 2PRA, and then minus a 0.52. If you just, actually you can put the 0.52 on the other side, doesn't really matter. Basically, we've gotten ourselves a quadratic to solve. The variable is PRA in this case, which you can just do a substitution. You can rewrite that as A or something if you want to. So you just need to solve this on the CAS. Let's solve 0.52 equals 3A and minus 2A squared. And we'll solve this with respect to A, and we get 2 values. It's not going to be 1.3 because we're working with probability, so it has to be 0.2. Therefore, it is option B. Alright, question 15. A probability density is given by this piecewise. The median of this function satisfies which equation? So which equation would the median satisfy? First of all, how is median defined on a PDF? It's the integral from 0 to m, where m is the median. In this case, we start at 0 here because that's where the function starts. Technically, it's negative infinity, but because it's 0 elsewhere over here, we can just chop it off at 0. So it's 0 to m of your PDF. So f of x dx equals 1/2. That's how the median is defined. So maybe let's plug that into the CAS and see what we get. So we'll do integral from 0 up to m of f of x, which is 1/12, times 8x minus x cubed dx. So this is the guy that we get, and what do we want to do? This is supposed to be equal to 1/2. Let's play around with this. So minus m squared minus 16. I'm going to bring the 48 onto the other side. So this is divided by 48, but we want to set this equal to 1/2. If you bring the 48 onto the other side, you're going to get a 24. Okay, expanding this out, what do you get? You get minus m to the 4 plus 16m squared, and looking at the answers, I'm just going to subtract 24 from both sides to give us 0. And let's try to match up the answers. So it looks like we want a positive. It's not going to be a and b with the negative m to the 4. So let's multiply everything by negative. So minus 16m squared, then plus 24 equals 0. So the answer is going to be exactly E. Alright, question 16. We have some Riemann sums here, so some rectangular approximations of an integral. So to do this one, you can use the programs, or you can just define a function f of x to be this guy and just evaluate at each of these points here and multiply by the width of each rectangle. A quick way to do it, if you have the programs, you just go down to Riemann sums, which is in integral calculus, Riemann sum. You plug in the function, which is 2 cos of 2x and plus 3, comma x, comma, we start at 0, we end at pi on 2. Number of partitions is 3. And we're using the rectangles are aligned to the right of the function. So we're going to go for option 3 here. And we get some answers. Now we want the approximation as a fraction of the exact area. So this program gives you the exact area and the approximated area. We want this as a fraction. So I'll take the approximated area and I'm going to divide that by the actual area, which gives us 7/9. So again, if you don't have the programs, you just have to do it a bit more of a manual way by calculating the area of each rectangle and then also calculating the integral area as well. Okay, the turning point of the parabola y equals x squared minus 2bx plus 1 is closest to the origin when? To do this, I'm going to define f of x to be equal to x squared minus 2 times b times x and then plus 1, just so we have a function to work with. And we want to find the turning point of this guy. Now, maybe you know the formula for the turning point of a quadratic. It's exactly negative 2 times the coefficient, negative the coefficient in front of the x there, which is negative 2b in this case, and you divide it by exactly 2 times a, which is 1. So that's going to be, let's think about it, that's just going to be b, isn't it? So we want the coordinates at b. So what's f of b first of all? It's that guy. And so what do we know so far? We know the turning point. The turning point is precisely b comma 1 minus b squared. Okay, and we want to find when this point is closest to the origin. To do that, let's just find the distance of this guy to the origin. So to do that, you can do, well, there's a couple ways. If you want to be extra fancy, you just use linear info. Then you type in b comma 1 minus b squared. And then, or actually, instead of typing 1 minus b squared, just type in f of b. And then comma 0, 0. And it gives you distance over here that you can work with. Or you can just calculate it manually using the distance formula. But essentially what we want to do now is we want to analyze this guy. We want to analyze this with respect to b. We want to find the value of b, for which this distance here is a minimum, it looks like. So analyze this, and it looks like we get local minimums at b equals minus root 2 and 2, or b equals plus root 2 and 2. So that should be c there if you just divide the top and the bottom by root 2. If you don't have this program, then what you could do is just take the derivative of this guy. So you need to solve the derivative of this guy equals 0. I'll do that quickly. Solve derivative with respects to b of this guy equals 0 with respects to b. You get a bunch of answers, and then you can just take a look at the graph of this guy, and you'll realize that b equals 0 is a maximum, so you don't care about that one. Okay. How many more questions to go? 3 more questions to go. Question 18. This one's a bit of a tricky one here, I believe. So we have some power functions. So x erases some power, and p, q are integers. So these guys are rational here. P over q and m over n. Now, whenever you have x raised to some power, hopefully you know what the graph of that looks like. It's going to look something of the following form. If your power is less than 1, then you're going to get some sort of square root shape. And if your powers are greater than 1, you're going to get some sort of polynomial shape like that. And you also get everything in between as well, like that. Okay. What do we know about this? We know that on the interval, by the way, that point over there where everything kind of crosses each other, it's always equal to 1, 1. If f is greater than g, so let's draw out some actual pictures now. So we have our axes. Let's do... Now, we know f is greater than g on 0 to 1. So what that means is we could have something that looks like this. So we could have f is greater than g means f has a power that's less than g. Not necessarily negative, because if f, for example, if f is a square graph, and you take g to be a cube graph, then g will always be less than f on the interval 0 to 1. So as long as the power of f is less than the power of g, sorry, am I getting this the right way around? Now I'm confusing myself. As long as the power of f is less than the power of g, this equality holds here. And just for illustration purposes, I'm going to assume that the power of f is less than 1 and the power of g is greater than 1, just so I guess it's easier to draw like this. Okay, so f is greater than g on the interval 0 to 1. So this is f and this is g. Maybe I use different colors actually so we can see things. So this is g and this is f. Okay, and the opposite holds on the interval 1 to infinity. So g is greater than f from 1 to infinity. Okay, so which of the following must be false? As we discussed before, the power of g must be greater than the power of f. Now, what's the power of g? The power of g is precisely m over n, and we require this to be greater than the power of f, which is p over q. So rearranging this gives us m times q is greater than n times p. So which one of the following must be false? It's not going to be c, because that's pretty much the equation we just wrote down, just in a different order. What else do we have? I don't think it's a and b as well, because if p and m are equal to each other, if p and m are equal, then you can kind of just ignore them, p and m, and you require that q is greater than n. So q is indeed greater than n, and so it's not option A. For option B, if q equals n, then you can kind of ignore q and n there. Let's try to zoom back in. You can ignore q and n, and you require that m is greater than p, which it is in that case. So it's not option B, therefore it's option D or E. For D, f prime of c equals g prime of c for some c on the interval 0 to 1. So on the interval 0 to 1 here, it's basically saying that the gradient is the same at some x value. In this case, it's going to be true, because you can definitely find, because the concavity is different on both of these functions here on that interval, you can definitely find some kind of value, c, where if you draw tangents there, the tangents are going to be equal to each other. So D is definitely true. You can also draw a similar picture for if you have like a square and a cube or something like that, and this also holds, because the concavities, you can find some gradients that are equal to each other. So it's not going to be D, and it's got to be option E. Because if you take a look at this equation here, this is saying that the gradients are the same, but your point is greater than 1. But if you take a look at the point at 1, well, the gradients of both functions, they're kind of diverging away from each other. So it's got to be option E. Okay, almost there. Question 19. The graph of f equals cos. So the cos graph is the bolded guy. So here's cosine. And then the graph of sine, that's going to be the thinner guy. So that's the sine there. An integral expression that gives us the total area of the shaded region is, looking at A, that's the integral from 0 to 3. So the integral across the whole range of sine minus cos, that's not going to be it there. Because, well, your area is kind of going up and down. The functions are interweaving. So you're going to get sines, areas, and all that adding up, which you don't want. So it's not A. Is it B? So B is the integral from 5/3, which is here, up to 3, and then you're doubling that. You could probably check, but I doubt that's going to give you the same area. So let's take a look at C. C is the integral from 0 to 1/3. So this C looks nice because you're actually splitting it up across these intersection points here of cosine minus sine. So it's big minus small, so this is correct here. Then minus 2 cosine minus sine. So we're going from 1/3 to 1, which is 1/3 to 1. That's a bit funny. Usually I like to think about it as 1/3 to 1 does make sense because you're taking a look at this area here. Cosine minus sine. Now here, this is kind of the wrong way around because cosine is smaller than sine on that interval. But that's fine because it's counteracted by this extra negative sign that's out the front. So this integral, along with that negative, doesn't need to give us that little area there. And we're also doubling the area, which takes care of this other area down here. And then finally, we're doing the integral from 5/3 to 3 of cosine minus sine. This is raising eyebrows once again because we're supposed to do sine minus cosine because it's big minus small. But again, this is okay because there's an extra negative sign here that counteracts that. So indeed, this integral, along with that negative there, does indeed give us the true area on that interval. So I'm going to go with option C. Option D probably won't work because this is the integral from 1 to 5/3 of... And you're taking 2 of that, so this first integral is taking care of that those 2 red shaded regions are shaded in. And 2, yeah, that's not going to be it either, because 5/3 to 3, that's this big area, and then you're trying to double that to this area as well, it's not going to work. And E, that's 1/3, so cosine. So that first integral is fine. The second integral is also fine actually because it's sine minus cosine, so it's bigger minus small, and you're doubling that to account for both of these areas. But I believe the third integral is where things go wrong because you have cosine minus sine, which is the incorrect way around because cosine is smaller than sine on that interval, but that's not counteracted for by an extra negative sign out the front. So E kind of fails with this last integral, so we'll go with C. Alright. Final question, question 20. The differentiable function f is a PDF. It's known that the median of this PDF is at x equals 0, and we also know the gradient at 0. Let's draw out a bit of a picture. So here's my x-axis with a 0. We know, first of all, it's positive at 0 because it's a PDF. PDF is always, the values are always 0 or positive. So x equals 0, the gradient at 0 is 4. So it's some kind of steep gradients like that, and then we could have it's just some wiggle, I guess. There's our PDF, doesn't matter. Let's draw a bit of a nicer one. So maybe something like this over here. Doesn't really matter what the PDF looks like. Actually, it kind of does because we want the median to be 0. So something like that. So there's my ugly PDF there. The transformation T maps the graph of f to the graph of G, where G is also a PDF with median 0 and G prime of 0 equals 1. So this is f here. And now I'm going to map it to another graph, also with a median at 0, but now the gradient at 0 is -1, so it goes down at, yeah, it's less deep than this gradient we had above here. And we want to find the transformation that does this. Okay, so first of all, looks like we have some kind of reflection in the x-axis, because there's a gradient here. It's going from positive to negative, so the only way that could happen is if we reflect in the sorry, did I say x-axis? I meant a reflection in the y-axis. So trying to get a shape that, yeah, looks like this over here. Okay, so it can't be a reflection in the x-axis, because if you're reflecting the x-axis, then all these positive values become negative, so that's not good. Therefore, we want to get rid of everything with a reflection in the x-axis. So we want to get rid of e, because there's a -2 in front of the y. And we want to get rid of b as well. So now we take a look at a, c, or d. Okay. We want a reflection in the x-axis. It's not going to be c, because that is not a reflection in the x-axis. So now we're down to a or d. Now let's think about this. If it's a, then we grab this gradient of 4 here. We're going to reflect it in the x-axis. So it's going to become, so a gradient of 4 here, reflected in the x-axis becomes a gradient of -4. Then we dilate from the y-axis by a factor of 2. If you dilate this gradient by a factor of 2, that gradient is going to become a -2. And then finally, you dilate from the y-axis by a factor of 1/2, which means swishing your y values down, and you can imagine what that would look like. They'll turn it into a gradient of -1, which matches what we have here, which is good. Let's just make sure D is the incorrect one. So we start off with a gradient of 4 at 0. We reflect in the y-axis, which gives us a gradient of -4. We dilate by a factor of 1/2 from the x-axis, which is bad, because if you swish all your x values together, you're going to increase your gradient to -8. And then further, you're applying a dilation by a factor of 2 from the x-axis because of 2y, which further increases the gradient to -16. So that doesn't match the gradient that we want, so we're going to go with option A. Also notice all of these, if you multiply these dilations together, they give you 1 or -1. And why does that make sense there? Because if you multiply your dilations together, that gives you the total factor in which your area changes, your unsigned area changes. And because we are working with a probability density function, the area should always be 1. So it makes sense that if you multiply these dilations together, they always give you plus or minus 1, which means the unsigned area underneath the PDF remains fixed at 1. So yeah, we'll finish off with A. Okay, so that's basically the whole multiple choice section there. It wasn't too bad, I found. Maybe definitely this one down here. The question 20 would have been a bit of a tough one if you didn't know how to interpret things correctly. Question 18, I also remember this one being a very tough one for a lot of people when we were doing practice exams. Yeah, I remember someone came up to me in year 12 and asked me about this question here in the library or something, and I was confused for like 10 minutes or something. So that was a very tough one. Yeah. Question 19, you have to be a bit careful. What other questions were tough? Some of these, like question 15, might not have been so straightforward if you didn't know the answer yet. Question 12, you do have to be a bit careful, I believe, because you want to account for white, red, and then red, white. So both possibilities there. What else was tricky? Question 11 could have been a bit of a trickier one as well. Some of these other earlier ones were pretty standard type of VCAA questions. So yeah, pretty good exam overall. So plenty of people would have done quite decent with this one. And yeah, hopefully this video helps you guys, and hope you have a wonderful day, and I'll see everyone in the next video. Bye bye.